Hi everyone, my name is Moyo and I'm a team member of this amazing group. I have here with me.
Hello, I'm Gabin.
Hi, I'm Daphne.
I'm Grace Kihozo,
And now,
I'll be joining them online.
Now we're going to explain to you how we discuss the prompt in our group meetings. We've had 2 meetings so far, and I'm going to hand over to Tuna.
Thank you. I'm going to share my screen. Yeah, so I'll share my screen. So as you can see, for question 1, the prompt was to have a logic circuit to show whether 2 bits were equal or not, and one could strictly be a not get. So what we have here in the document. So yeah, what we have here in the document is a demonstration of 2 bits being equal. So the get that you can use to get this is X NOR get, or it's a XOR get combined with a NOT get. So when A and B are equal, the output should be 1, but if they're not equal, then the output will be 0. So if you have two zeros for A and B, then the output will be 1. If you have 1 and 1, then the output will be 1. Otherwise, it will be 0. So Gabin will go ahead to demonstrate this on logic.
Yeah, I can show how we draw a logician from this truth table. So we had like to do it using 2 gates. Strictly when one needs to be a NOT gate. So we used firstly an XOR gate and connected the output with a NOT gate so that we get the intended output from the truth table. So let me start. When the first input is 1 and another input is 1, we need to check the output so that we know that both of the inputs are equal. So as you can see, when both of them are 1, the output is 1. So let's try when one of them is different. One input is 1 and another one is 0. So when I do that, you see it's 0. The output gives us 0, which shows that like the 2 inputs bit were totally different. So let's try and when both are 0, our both inputs are 0. So when both inputs are 0, you can see that we have a 1, which means that both our inputs were 0. So on the circuit board, because the NOT gate was not working well, had to implement this directly using an XNOR gate. It does it the same, where the both inputs when are the same, equal, we have 1. When one of them is different, so when the 2 of them are different, we have 0. And when they are both 0, which means they're equal, we get 1. Yeah, so this was the basic logic we used to get to check if 2 bits are equal. There are a lot of ways you can do this using other gates, but we chose this one because it was more very understandable. Yes, thank you very much. Let me hand it to the question.
Thank you very much, Gabin. So in the meetings recordings, I and Grace worked on question 2. So for question 2, we were asked to design a 3-bit full ADAS circuit where 1 bit is strictly logic 0, low all the time. I'm going to explain the approach we took while Grace is going to show you through the demonstration with Logizen. So in designing the 3-bit full ADAS circuit, we use the normal full ADA table, which is the table which you can see here. We have the 3 bits A, B, and C in. C in stands for the carry input, while we have 2 outputs, which are the sum and the C carry output. So the way this table works is when we have 0 plus 0 plus 1, we have the sum as 1 and we have the carry output as 0. So the sum can only be 0 and 1. If we have a sum that is 2, we have to write 0 and then carry 1. So A restriction that was given for this question was that one bit has to be strictly logic 0, which meant that this entire Cin, as you can see here, had to be strictly logic 0. And so when we change this to 0, and we have everything as strictly logic 0, we're going to have some duplicates in our truth table. So as you can see here, we have these two tables being duplicated, we have these two tables being duplicated, and we also have these two tables being duplicated. And in order to avoid having two inputs in our truth table, we had to remove one of the duplicates. So after removing the duplicates which we have this resulting table here. So through this table, we have only one set out of the duplicates. So this is the truth table of a 3-bit full adder where one bit is strictly logic 0. And in building the logisim, in order to basically get logic gates that can help us that was derived from the sum and the carry output, in order to get the sum, we had to do A, X or B, X or C. While in order to get the carry output, we had to do, in order to get the carry output, we had to do the sum XOR, sum and A. So initially we had this table here. I'm just going to demonstrate to you this first one while Grace is going to demonstrate the second. So initially we had this resulting logic gates when I put 0. So when we have 0, 0, 0, we have the sum to be 0 while we have the carry output to be 0. And if we compare that to our truth table, it is actually correct. When we have B to be 1, we have the sum to be 1 while we have the carry output to be 0. When we also have 1, so when we have just one high, we have the sum to be 1 while we have the carry output to be 0. If we have A and B to be 1, the carry output is going to be 1 while the sum is going to be 0. So we can see here that this actually corresponds. So we have A and B to be 1, A and B to be 1. We have the sum, which is equals to 0, and then the carry output, which is equals to 1. So in building this first gate, while we were wiring our kit, we didn't have enough connections. So we didn't have enough of this. And then also, we didn't have enough XOR gates. So in order to do that, we had to implement this second table, which is basically the sum was derived as a result of A, X, or B, X, or C, while the C out was derived as a result of A and B and the negation of C. So Grace is going to walk you through the demonstration of this.
So I was muted. As you can see, if A is 0 and B is also 0, then and C is also 0, then the sum will be 0 and the carry output will be also 0. And when we also, like when we have A 0 and B is 1 and the C in is 0, then the sum will be 1 and the carry out will be 0. And when we have A as 0, but then B is 1 and C in is 0, then the sum will be 1 and the C out will be 0 as well. When A is 1 and B is 0 and C in is 0, then the sum will be 1 and the C out will be 0. And when we have A as 1 and B 1, then C in 0, then the sum will be 0, and then but the carry out will be 1.
Thank you very much. So through the demonstrations, we're going to walk you through how we basically wired our kit now.
Immediately the to compare both inputs, if they are equal, we're going to use the XNOR gate to show that both inputs are 0. So we are going to start when both inputs are low, which means are 0. Yes, we connected with the XNOR gate. And then we connect the output to see like the final results. Then let's connect the battery to see it. Yes, so this light means that the final output was 1, which means that the two inputs we inputted are equal. So let's try when one is 0 and another one is 1. So which means that two different bits, which means the final output will be 0, which means that they are not equal. So let's try one more time when both input bits are high, which means that both are 1, to check that they are equal. Yeah. So we got 1 because the two inputs were 1 and they are equal, which means that the output gave us 1, which means the two inputs were equal. Yeah, that's how we could check this, like how we can compare two bits and find if they are equal. Yes. Let me pass.
Thank you very much, Gabin. So I'm going to walk you through how we did question 3, designing a 3-bit full adder when 1 bit is strictly logic 0. If you can see this gate here, so I'm basically going to be building this gate whereby the sum was created as a result of A XOR B XOR C, while the C output was created as a result of A and B and C negation. So because of the limitation of the board, as you can see here, we don't have enough connections, which is why I'm going to first connect the sum and then first connect the output. So starting with my logic inputs, I'm going to have 3 connectors. I'm going to first test it when A, B, and C is 0, so when they are both low. So we're going to have A, B, and C. So if you can see here, they are on the low inputs. Then I'm going to connect these 3 to the XOR gate. So connecting it to the XOR gate, we're going to connect it here. Then we're going to connect this here. Because we have 3 inputs. Then I'm going to use the second connector to basically connect here and then connect to the output. So this is going to give us 0, as we've seen on the truth table. So as we can see, we don't have any lights, meaning that it is 0 and our first gate is complete. So this is the gate for the sum, and this is basically what it gives us. I'm also going to try it when we have B to be 1. So when we have 1 to be high, our sum is going to 1. So this is going to light. As we can see here, we have the resulting outputs which you have. So A is 0, B is 1, and then C is also 0, which basically gives us our sum to be 1. Then when we also have A to be 1, so I'm going to move this. So this is A, if you can see what is written here. So when we have that to be 1, so when we have A to be 1, as we can see, it gives us a light, which is whereby our sum is 1. But if we have 2 of the inputs to be this, then we're not going to have any output. So with this now, we've successfully tested the XOR gate for the sum inputs for designing a 3-bit adder whereby 1 is strictly logic 0. I'm going to take you through how we get the C out. So in getting the C out, we need to have 1 input to be A. We need to have 1 input to be B. We need to have 1 input to be C negation. So we put it here. C, let's have it here. so low. So this here is going to be C negation. So we're going to put that here and then connect this to NOT gate. If you can see, this gate is NOT. Connect it to this gate, then connect this one. So now these two gates are going to connect to an AND gate. So here and also here. Then we're going to connect negation of C back to the AND gate. And then this AND gate, we're going to connect it to the input. So with this here, we're meant to have, when A is 0, B is 0, and C is 0, our output is meant to be 0. So let's see what that gives us. Correct, and as you can see, we don't have any lights, meaning that the output is 0. Let's try it when A is 0 and B is 1. So when A is 0 and B is 1, our output is also 0. This is lighting because we said A is 0, because we said, so A is 1, B is 0, and also C is 0. So as we can see, the output here is 0, meaning that this works perfectly. Then we're going to test it when two of our inputs are high. So when this is high, we're going to have 1. So when A is 1, B is 1, as we can see, this is lighting because A is 1, B is 1, and our C negation is basically 0, then our output is meant to be 1. And with this, we successfully tested the logic gates for the C output and the sum. Thank you for watching our video. This is our team again, and we hope you enjoyed our presentation.